Recording in progress.
Hey, good afternoon, everyone. So we're very happy today to have our own Grigory, who is going to tell us about field theory behind geometry part 1, smooth sets of fields. Grigory?
Hi, everyone. Thank you for coming. So today I'm going to talk about, obviously, joint work with Hisham and Urs. So this is based on the first part in a series of papers we're planning. It should come out very soon. So the plan is roughly, so we're thinking how to present this. And it seems there is people from physics who wouldn't know this categorical stuff, and also people from maths who wouldn't know the physics concepts. So I decided to be very basic in both ways, so that at least everyone will get something out of it, but really get the gist of what we're doing here. Okay, so what is actually the plan? Okay, so I'm gonna recall the description of classical field theory, the textbook description. So talking what are fields, the space-time and fields on it, and how do people derive the equations of motion, so the Euler-Lagrange equations from a local action functional. So I'm gonna go through this description without defining what we mean by some terms. And then the goal will be to find an appropriate category where all this, in particular, smoothness of all these objects and maps takes place in. So after this description, I'm gonna collect some desired properties of the ambient category where this description of classical field theory should really take place in. And we're gonna list them one by one. Then I'm gonna try and describe a notion of generalized smooth spaces as something that can be smoothly probed by simpler test spaces. So smoothly probed by finite dimensional manifolds in this sense. So this is functorial point of view on geometry. Should go back to Grothendieck at least, I think, and people who are experts should correct me. So this, by looking at this intuitive blah blah and looking at it and trying to make it consistent, we will see that you immediately arrive at the definition of a smooth set. So it will be this kind of generalized smooth space that we're talking about. It will be a smooth set. We'll define it properly. Okay, and lastly, having the definition of this generalized space, I will indicate how this kind of, it's called the sheaf topos, the collection of these spaces forms a category. It's in particular sheaves over something. I will define everything. And I will indicate how this naturally hosts, in particular, the variation of action functionals in field theory, the smooth spaces of fields, the infinite dimensional space of fields, and many more field theoretic notions. Okay, and by the way, please just stop me if something is unclear or I assume something or something is too clear. Just stop me so we can discuss and get through everything. Okay, so let's start maybe with something super simple. Let's start with the description of the critical locus of some smooth function in finite dimensions. Okay, and this is the sort of archetypical picture of physicists have in mind when they talk about field spaces, and then they have an action functional on them, and they vary it in some sense, and they find the extrema, which are the classical fields, classically physically realizable fields. But this is a toy picture which is rigorous. So we'll start from that. So what is the data that comes in? Well, it's a finite dimensional smooth manifold, which should be viewed as the kinematics of the theory. So the possible configurations of the system, and the dynamics of it are dictated by a smooth function from the configuration space into the real numbers. So this should be seen as an action function in finite dimensions. And one says this is just geometry. A point in the manifold is a critical point if the composition of F is a critical point for F. If the composition of F with any path passing through that point P has derivative 0 when evaluated at that. Okay, so I'm writing it in this sense. This is equivalent to saying that the differential of the function is 0 at that point. Okay, this is very trivial, but they're equivalent, but they're not necessarily equivalent in infinite dimensions once you leave this realm. That's why I'll focus on this condition. Okay, so it just says, well, go through any path through that point and take the derivative. Well, that should be 0. So this is stationary condition. Right? So a point is critical if this is satisfied for all curves. Now, the set of critical points, well, it's just a collection of these critical points. So in particular, it's a subset of the manifold viewed as a set. And it's called the critical locus of f, of the function f. And alternatively, if you want to be slightly more categorical, this is an intersection, right? So it's an intersection, can be viewed as intersection of two sets, not manifolds per se, but what you're doing is, well, you're taking your configuration space N, let's say, then you're mapping it into the cotangent bundle via the differential of f. So this is just a section of the cotangent bundle. And then you also take the 0 section, and you're saying, well, which points are critical? Well, there are those that their image coincides under these two maps. So it's a pullback in categorical language, but it's computed in set, meaning that, well, even though all these guys are manifolds, this intersection of these two, of these two maps inside the cotangent bundle might not be a manifold itself. So if the intersection is not transversal, for instance, it will not be a manifold, a finite dimensional manifold. Okay, so this is the finite dimensional picture. This is everything is well defined, this standard textbook stuff. And physics usually goes off like this, okay? But well, classical field theory at least. Okay, so what do we do? Well, we start with the kinematical data. Before we just had the configuration space in manifold. So the analog here is built up out of sections of some fiber bundle over space-time. So what do we do? Well, we fix space-time. Okay, so it's a finite dimensional manifold. You can take it to be Minkowski space, Lorentzian or no, it doesn't matter. And you fix a field bundle, so a fiber bundle over this manifold. So this could be SU2, or it could be some vector bundle for some ON models or something for the physicists. But in any case, it's some fiber bundle, might be trivial or not. And then a field, a single field, is a section of this bundle. So the so-called off-shell, for reasons that will become clear shortly, the off-shell space of fields, really a set at this point, it's not a space in any sense, but it's a set. It's just a collection of sections. So it's a set of sections of this fiber bundle. Local or global, let's not worry, okay? It just says, well, at any point in the space-time, you assign a value over it, over the fibers over it, right? So for instance, for the electromagnetic field, if you want, you could take this to be, let's say, the cotangent bundle and so on. So locally you have a one form, right? So it's each point it assigns a one form and so on. Or for instance, if you take the bundle over it to be just M cross the real numbers as here, well, then sections of this trivial bundle is just smooth functions, real valued functions on the manifold on space-time. And this is the off-shell space of fields for scalar field theory, right? It's just a scalar field, just a real smooth function. And the full space of fields or set of fields is the collection of all possible sections, right? So this is just kinematics. There's nothing to dictate what is a classically, physically realizable field configuration or something, right? Again, the dynamics comes as follows. Well, then this is how it goes. The Lagrangian density should be a smooth map, in a sense that's not defined yet. It should be a smooth map that assigns to any field configuration. So for any field, you write such an expression, right? And it assigns a top form, so a density on oops, sorry, what did I do? So a top form, a density on space-time, which you can then integrate to get the action function. Locally, you usually write this as such, right? You pick some coordinates on the base, and you have some coefficient here that depends on the field, and then you get a top form which you can integrate for any field, for every possible.
Sorry, Gregory, it seems there are questions online.
Oh, yeah.
What makes this off-shell?
Yeah.
Just that we're not doing it relative to boundary.
No, so he can hear me, right? Yeah. So off-shell will be defined shortly by defining what is on-shell. So it comes from physics terminology. So the space of on-shell fields, or the set of on-shell fields, will be some subset of fields that satisfies the equations of motion, the classical, some PDE. So it satisfies some extra conditions that is dictating the dynamics. So that will be those fields that satisfy the Euler-Lagrange equation will be called on-shell. So then physicists call things that don't satisfy the classical things off-shell. Okay, so I think that's the correct description. Now there is some history about the shell, right? Which I don't recall. It comes from German or something, right?
No, I think this comes from the math.
Yeah.
This comes from the math.
Yeah.
Actually, do this for single relativistic particle for fixed mass. It sits somewhere on this hyperbola.
Right.
And you think of this hyperbola as a shell.
That's right. Yeah.
Mass
Yeah. Yeah. That's right. Is that okay, David? I cannot see the conversation. So.
Yes, that's great.
Yeah.
Thank you. Great. Thank you.
Oh, cool. Nice. All right. So the dynamics that are dictated by Lagrangian density, all right? So it should be smooth, and furthermore, it should give an action functional by integrating this, by composing with integration. So it should end up with a real number, and this should be smooth as well in a sense. By the way, let's not worry. This might not be defined if we're working over non-compact space-times, but it will be defined for compactly supported fields and so on. But you don't need to worry. You really work with this. But let's pretend it works, and we're over a compact space-time such that we can get a similar picture to the finite dimensional case where something is valued in the real numbers. So it should be a smooth map, right? So you just take a field, apply the Lagrangian density, and then integrate. So you get a real number, and it should be smooth. And furthermore, in fundamental field theories, the Lagrangian is local. In a sense, to be made precise, but when you write down coordinates, it depends only on derivatives of the field at each point. But more mathematically, they should say that the Lagrangian itself should factor through as such a composition where you take, well, a field, a section of the bundle you started with, and you take the jet prolongation. This extracts, let's say, intuitively the derivatives of the section. So it gives you a section of the infinite jet bundle over it. I'll say something about it later. And then it's actually given by composition with a bundle map out of the infinite jet bundle into the top exterior power of the cotangent bundle. In any case, there should be such a factorization, which basically says, if you look at it, stare at it in local coordinates, it should give you the formulas that you want in physics, right? That depends locally. It depends only on the field via its derivatives at each point. Okay. All right, so this is the point is that all fundamental physical theories are of this form, okay? So if we were to talk about field theory, we want to encode this locality as well, and it should be smooth as well, such that we can argue about variations and so on. Yes?
I've seen similar setups in other situations. People just go directly from smooth maps to fields and then factor through topical for them. So what we practically get by factoring through topical?
Yeah, so I mean, what do you get? The point is that we want to encode this story that I will get through in a moment. Okay. And you will see why. I mean, that's the point is that in the end, you want to encode field theory, and it's not like you want to get something out of it. This is how it appears. Field theories appear by, and you have a space-time, and then you integrate something over it. And this is the action function of it. So, I mean,
So one could say these are the Lagrangian theorems that arise this way.
Right.
The Lagrangian theorems about this form, this top form, is the Lagrangian density.
yeah.
And you may have field theories that are not Lagrangian, but most of them are.
Yeah. So fundamental field theories are Lagrangian, but you could say, okay, let me not care about these guys, all right? But just say, okay, I have a space-time, I have some space of sections, so fields, and I say, okay, the dynamics are given by some PDE, right, on them. Right. And this, it might be that it doesn't come from a Lagrangian by variation. That's all. But for fundamental field theories, it comes from a variation, right? Meaning, I'll tell you now what it means. Well, then, for a field to be on shell, so remember we had all this space of fields, set of fields. Well, this is called it on shell if it is a critical point of the action functional in the sense as in classical, as in finite dimensional geometry. So you take, if this is satisfied. So if for all smooth curves to be defined in field space, well, then you take the composition of the two guys, then what you end up is with, well, you compose here, you get a map from the reals into the reals, it should be smooth, and then you can take the derivative. But you see all sorts of little things come in. You should define what you mean by a smooth curve in field space. So that's also what's missing here. And physicists just write this kind of this thing in gray and pop like they just do algebraic manipulations. So, so this is what a field, what it is to be on shot. It is that it's an extremal point of the action function, or Lagrangian if you don't want to integrate. Okay, so now if the Lagrangian is local, so if it factors through the infinite jet bundle, then you can express this condition in a more down-to-earth manner. If it is local, then you can go through some, well, algebraic manipulations, more or less, and bring it to this form. Okay, this derivative, which is what? Well, these are the so-called Euler-Lagrange differential operator, which corresponds to the chosen Lagrangian, applied on the field phi, where the curve starts from. And this is that you can interpret it as a tangent vector attached to that point. So in any case, there is a non-degenerate pairing between this guy, and this should hold for all such curves, i.e. for all such tangent vectors. So this being 0 is equivalent, modulo minor analytics, to this, to the field equations. These are the Euler-Lagrange differential equations, let's say, which correspond to the Lagrangian. So doing this in local coordinates, what you end up with is that, well, this Euler-Lagrange differential operator, it looks like this, right? The standard partial derivatives and some abuse of notation going on, but this is what it looks like if you want to. But what is it really? Well, it's a map. It takes a field, right? Field configuration, and it maps it to a section of this bundle, if you really want to be precise. So what do you get? Well, you get something that is valued in the dual of the vertical fiber bundle of F, tensor some top form, and this guy here is something in the vertical fiber bundle. So you pair the two things by duality, and then you integrate the top form. So it makes sense. But if you look at the local expressions, you can deduce what this is as well. Okay, so this is the Lagrange differential operator. So in other words, well, the extremal condition is equivalent to the field satisfying the field equations. So you can write it, if you want, as an intersection or as a pullback, again, like in the finite dimensional sense, where the critical set, well, it's isomorphic. Well, it is the space of on-shell fields, which is given by, well, the fields that vanish under the Euler-Lagrange differential operator. In other words, you can write it as such an intersection. Well, you take F, you put in the corners your field space, and then, well, on the one hand, you have the 0 differential operator map, and then you have the Euler-Lagrange differential operator, and you take this intersection in sets again, right? So I write here T star F var something. It's just a definition. Instead of writing this whole thing, well, you can notice there is a projection from this guy to this guy. So really, it's a replacement for the cotangent bundle in finite dimensions, but this is only for local variation of field theory. Such a picture, for instance, doesn't hold if you don't factor through the jet bundle, because you cannot do this. So it's called, we call it, or more people call it, I don't know, the variational cotangent bundle. Okay, so this brings it to, this story. Okay, it brings it very close to the finite dimensional picture, but we have not really defined what we're talking about. We have some smoothness of the field space, and then we consider smooth curves in it, such that compositions with this smooth Lagrangian become smooth, and then we can take a derivative of a smooth function in the real numbers. So that's what we did, and now we're gonna indicate what we actually need out of this, right? So what did we assume is happening? Well, we assumed some generalized notion of smooth spaces, which must have the following properties. Well, the mapping spaces between smooth finite dimensional manifolds should be some kind of generalized smooth space in this sense. In particular, also sections of bundles should be so. This infinite jet bundle that I talked about should be such a thing as well, because we're talking about maps between them and sections of it. So this infinite jet bundle, well, I'll talk in coordinates a bit more later, but it's a limit of finite dimensional manifolds. So it's a limit of increasing dimension. So in particular, it cannot be a finite dimension manifold because the dimension increases. So it should be, in a sense that encodes also the formulas that we want. It should be this kind of generalized smooth space. Its space of sections should also be such a space, such that furthermore, this jet prolongation map that I wrote down is also a smooth map. And furthermore, that smooth bundle maps that I wrote down before should result into smooth Lagrangian densities by precomposition and action functionals, which contain all the forms that we have in physics. So it shouldn't be some arbitrary notion, but it should also produce exactly the things that people write down in physics. Well, furthermore, the smooth structure of the field space should allow us to talk about smooth curves in it. All right. So in particular, this should be also a smooth space in this sense. So these things should be well defined such that then this composition of the action functional with smooth one parameter families of fields, let's say, is smooth in the usual sense. So you can take the derivative. So you want all these properties, right? Okay. Any questions? Or let me say some more properties. Oh, go ahead. Yeah. Yeah. Yeah, for a single point, yes. I mean, what you're saying is that it's a limit of sets in that sense. But, yeah. Okay. But you can, yeah. So it's a bit right. I can say more about it. I'll come into it how we consider it. Yeah. But let me not. Yeah. I'll say a bit more about it soon. Okay. In particular, if this composition for any, so if this composition, right? So what was I saying? If we have a, this doesn't work. So if you have a one parameter family of fields, and then we compose the action functional, then well, we get a smooth function. We should get a smooth function. Sorry. A smooth function from the reals to the reals, so we can really take this derivative and evaluate at 0, and then the algorithm of integration by parts should be rigorous. So it should be if and only if this thing. Okay. And then as an extra point, really, we would like this critical subset not to only exist as a set, but actually as a smooth subspace of these of fields. Really, because in field theory, we are talking about, usually we're talking about, in classical field theory, we're talking about this subspace of on-shell fields, and people, argue about currents and charges on it, and these are really treated as smooth maps. And in this case, they do come out to be smooth, as I will indicate, in this sense that I will define. So this category that we're going to work on really allows to consider these critical these intersections as smooth sets as well. And lastly, and importantly, this is a clue, finite dimensional manifolds should really be faithfully included in this picture, right? The reason is why, well, from our point of view, well, I've described field theory as working over a space-time, which is a finite dimensional manifold. But if you take the space-time to be a point, then all this discussion collapses to the finite dimensional story. So if this is to be consistent, then all the story should just reduce also. All the operations we do in smooth sets should reduce to finite dimensional manifolds if we work with finite dimensional manifolds. So finite dimensional manifolds should also be viewed as smooth spaces in a precise sense, okay? All right, so any questions? Now we can do maybe some maths. No, okay. Okay, let's try to define this, and we'll do it in a very sort of intuitive way, and we will get the correct definition. So what is the basic idea? The basic idea is the following. It's not to say, okay, let's start with a set of points, of underlying points, and then put some structure on it, and on some charts that on intersections, they have diffeomorphisms or whatever, or infinite dimensional charts, or if you want topology and so on, plus stuff. So you don't want to do that, but you want to define this notion of space purely operationally by just saying, what does it mean to smoothly probe this would-be space? So by assigning, what would it mean to have a smooth map from a finite dimensional manifold into this would-be space, right? So this is this functorial point of view in geometry. All right. So for instance, for a manifold sigma, for a finite dimensional manifold sigma, and X, this curly X will denote the would-be space, to be smoothly probed, we should think of a smooth map, whatever this is going to be. It's not yet defined, but a smooth map from this finite dimensional thing into this arbitrary generalized space. It should be thought of as a smooth sigma-shaped plot in X, right? So you think roughly, well, you have something that you know how it looks like. Well, you map it into something that you don't know how it looks like. Well, what does it do? If you smoothly do it, then it should map some smooth sigma-shaped plot. So we're gonna call this such maps into X to be defined. We're gonna call them sigma-shaped plots or sigma plots or plots from sigma into X and so on. So this is the rough intuitive picture. And now we want to say, okay, what are the conditions that we get that we should impose such that this is consistent? Okay, this kind of rough picture up to now. All right, so the first consistency requirement, well, I'm not really consistent, but just what did I say in words? I said, well, for any this kind of test probe, so we're gonna test these generalized spaces with manifolds, finite dimensional manifolds, which we know about. Okay, so we just said that for any probe sigma, finite dimensional manifold, there should exist a collection of smooth sigma-shaped plots. So just the sentence just says, well, there should exist a set of sigma plots in X. So it should be for any sigma, there should exist some set. Well, we can say plots of sigma into X, or just denoted by X on sigma, suggestively, and this should be a set for any sigma, right? So there should be an assignment for any sigma in manifolds. There should be a set of plots, for instance, right? So if you take sigma to be a point, then the plots of a point into this generalized space, that we should really interpret it as the points of the point plots of X, i.e. the points of X. Or if you take sigma to be the line, which we really want for the variation in particular, well, the plots of X should really be should be considered as the smooth lines in X. Right? Okay, so this is one condition. It just makes into mathematics what we said, right? It says, well, for any manifold, we should have a set which we interpret as sigma-shaped plots in X smoothly. And what is another condition that intuitively comes out? Well, let's say we have a smooth map between finite dimensional manifolds, sigma prime into sigma, which we know what it means. A smooth map is whatever we mean by manifold smoothness. In charts, it's smooth in the Cartesian sense. Well, then we can write down this diagram, which we have not yet defined, but we can write down this diagram. And well, if we had a sigma shaped plot phi sigma into X, well, then we could expect to be able to pre-compose by this smooth map, right? To produce a sigma prime plot in X, okay? But this should happen for any phi sigma. So in particular, there should be a pullback map, right? That is to be interpreted as this precomposition that takes sigma plots, well, and then precomposes, let's say, by this map, and it gives you a single sigma prime plot, all right? So not only do we have an assignment of plots for any test manifold sigma, but we also have a pullback map for any map of probe spaces, manifolds. But also intuitively, you would expect these extra two conditions, which almost nail down the definition. Well, if I just put the identity here, if I put sigma, if I put sigma here and the identity of sigma, well, then precomposing by the identity should really do nothing, right? On the probes of X. In other words, this pullback map corresponding to the identity should be the identity on the probes, on the plots of that probe. And furthermore, if you compose with two, if you take the pullback of the composition of two consecutive maps of probes, well, then this should be really the same by doing the pullback consecutively. Right? This is just for these diagrams to make sense to you. But if you just stare at these two things, what we just said is really that X is a functor, right? A contravariant functor from the category of manifolds, right, into sets. What does it do to any manifold? It assigns the sigma to any manifold sigma. It assigns the sigma-shaped probes, smooth probes, and for any smooth map between manifolds, you have a pullback of probes. So this is really a contravariant functor. So in other words, people call these kind of things pre-sheaves on manifolds for those who have not seen it. For those who have seen it, I'm sorry, but everyone needs to see it. Okay. All right, so just thinking about what would it mean to probe something, you automatically get such a definition, right? But we want an extra condition. That's not all. We also intuitively we expect the following, right? So let's say we have a probe sigma and we have two open, you have an open cover by two open subsets, right? So just cover it by two open subsets. And let's say you have two plots from the smaller neighborhoods, each from the smaller neighborhood, such that if you restrict them by these pullback maps on the intersection, then they agree. Well, then you expect if you have two plots that agree on the overlaps, that you should be able to glue them to a bigger plot. Okay, this is the shift condition. I'm not gonna go through it in detail, but you can just say, well, if you have a big and open cover by an arbitrary family, then this pullback map that I described before for this map of manifolds, smooth map of manifolds, this projection, then the pullback map should be a bijection. All right, let me not go through it, but it just says you should be able to glue plots from smaller plots to build bigger plots. Now this is called the shift condition with respect to open covers for manifolds, let's say. If you put together these three conditions that just come out by, well, what we would want of this kind of notion of spaces, well, you get the notion of a sheaf on manifolds. So we define a smooth set. This is our definition of this generalized space as a sheaf on manifolds with respect to the open coverage. So it is a pre-sheaf such that also you have this gluing condition on plots. Any questions here? I hope people are not just sleeping. But, okay, well, all right. So we have defined the notion of smooth spaces, this kind of smooth sets, and now we also, well, if we define smooth sets, we need to talk about how to, well, smoothly map one to each other, right? But what we have, this notion of smooth spaces, all we have is their collections of sigma-shaped plots on it, right? So what can we define a smooth map to be between two things like this? Well, it should take smooth plots of one to the other, right? So a smooth map from X, a smooth set to Y, another smooth set, so two sheaves. Well, it should take the sigma-shaped plots of X to the sigma-shaped plots of Y for any sigma. And furthermore, it should do it consistently with respect to pullbacks of probes. But let me not go through it. I mean, if you stare at it, you would expect this to commute. What you get is a definition for our category that we should work in, and I'll explain why we should work in this. This is the category of smooth sets. Well, it's just sheaves on manifolds, and maps between them are functors, natural transformations of functors, right? And these are sheaves with respect to the open coverage. Okay. All right, let's see an example. Maybe people will wake up. All right, so we've talked about this generalized notion of smooth sets, but actually, as these spaces which can be probed by manifolds, finite dimensional manifolds, but it turns out, well, very naturally, any manifold can be itself viewed as such a thing. And how do you do it? Well, how do you guess you would do it? Well, you get take any manifold, and you want to define a smooth set corresponding to it. Well, what would this be? You need to assign, for any other manifold sigma, you want to assign the ways to smoothly probe M by sigma. Any guesses how to do this? No? This says everyone is sleeping. Well, anyways, the way to do it is, well, you have two manifolds, and you want to say, how do I smoothly probe M with sigma? Well, these are manifolds, finite dimensional manifolds. You know how to do this, right? You know what it means to have smooth maps between two manifolds. This is just the set of smooth manifold maps from sigma into M. This consistent assignment for any sigma, it will define a smooth set just by construction. Right? In particular, this is the Yoneda embedding. And it comes with a consistency condition, which is a Yoneda lemma. And it is the following. Well, now we have a notion. Let's say X is any smooth set, okay? And M is a manifold. Well, now I know what it means to have a smooth map from the manifold M into X. Why? I just view the manifold as a smooth set and then consider smooth maps that I defined before, these natural transformations, just working on plot-wise. But then, well, I have this notion of smooth maps, but I also considered really the plots of X by M to be smooth things, in a sense, smooth maps. So if these weren't the same, then our definition would just be bad, right? We would contradict ourselves. Okay, but they are the same actually. So good. The UNED lemma just says, well, if you want to view the plots of X as smooth set maps from the embedding of M, it's the same as just taking the plots originally used to define X. Okay. In particular, if you want, well, if you take X to be another manifold as a smooth set, well, this just gives that the smooth set maps between the two manifolds as smooth sets is the same as the maps of manifolds. So there's no extra maps arising by going into viewing manifolds as smooth sets. So indeed, what this says is that what we wanted, one of the properties that manifolds, finite dimensional manifolds, do live in this generalized notion of smooth spaces faithfully. So there's, if you consider them as smooth sets, it's not like new maps will appear or anything. So whatever we do will include what we described before in finite dimensional geometry. Okay, maybe let me go through this quickly because everyone is, so I go back to physics. Anyways, the point is that we can simplify the site. The definition of a site, which I didn't say, is whatever we use to probe. So it is the collection of probe spaces supplied with some notion of coverage. In our case, it was manifolds with this open coverage. But if you stare at manifolds, well, you know, by definition, any manifold is covered by Cartesian spaces, right? So it has an open coverage by Cartesian spaces. And Cartesian spaces, they sit inside all manifolds. They're just the simple manifolds in them. So it's a full subcategory. And if you stare at the shift condition enough, well, you can check that this induces an equivalency of categories. It just says, well, take any sheaf over manifolds and, well, just restrict it to probe it only with Cartesian spaces. And why is this an equivalence? Because, well, if I have such a thing here, a sheaf on Cartesian spaces, and you ask me, how do I probe it with another arbitrary manifold? Well, I just tell you, cover your manifold, right? And then use the shift condition on overlaps, since you know how to probe it with just Cartesian spaces. Okay, anyway, so this is a simpler definition, right? So we just need to probe it with Cartesian spaces. So we might as well define smooth sets to be sheaves on Cartesian spaces, period. We don't need arbitrary complicated manifolds. This just follows by the shift condition. So this Cartesian spaces just include, the real line, R2, R3, blah, 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 for any n. So it's much simpler than the whole of manifolds. And topologies are trivial and so on. So it's much clearer to think about how to probe a space with this even simpler spaces, just Cartesian spaces. In the end, what you get, the categories are equivalent. So you might as well work with this. Okay, so let's go back to physics and argue that any field space, as we define them, is really naturally to be viewed as a smooth set. And then we can do the physics story. All right, so smooth sets of fields. Well, let's assume now, for starters, that our bundle, the field bundle we start with, is just a trivial bundle, right? So we have a fiber n, and you just take m cross n, right? Then the section of this guy are just smooth maps between m and n as manifolds. So if you want, this is the configuration space for a sigma model with target n. Right? And we want to put a smooth set structure on it. So in particular, what should it do? It should assign to any Cartesian space something to be viewed as, well, for Rk, let's say, an Rk parameterized of smooth maps into n from n. But there is an obvious assignment like this, right? What do you do? Well, you take any Cartesian space and you assign it to which set? Well, the set of smooth maps from m cross Rk into m, right? So it is a notion of smoothly parameterized maps from n into n, because for each point x in Rk, well, you restrict and you get a normal map. And this is indeed a sheaf. It satisfies all the conditions that we don't need to go through. In particular, this gives a notion of a smooth curve, right? You can be more explicit set theoretically, but it gives a notion of, it identifies what it means to say, well, this is a smooth curve in the field space. Okay, I'll skip it. And furthermore, for an arbitrary fiber bundle, you can do the same kind of definition. You just take sections. Now sections are not just maps between two manifolds, but it's some subset of it. So what you need to do is you need to take, well, what is an RK parameterized section? Well, it's what you would expect. It's a section that is parameterized by RK. So it's such a map here. So it's this map, such that this triangle commutes. In particular, for each point X here, it gives us a section, a normal field configuration. And here's a fact, a general fact about this category, that for any kind of smooth set, as arbitrary as it can be, there exists a notion of a smooth mapping set between them. So, which actually recovers these definitions above. So they don't just come out of the sky. This is something that is very natural in this kind of categories, any kind of shift category. It's called an internal home, and it just automatically gives you this kind of mapping spaces with the smoothness coming in for free. You don't need to worry at all. You don't need to go and take this big set and try to put charts on it and so on. It works sometimes, but not always, and it's very complicated. So anyways, so we get our field spaces as smooth sets, okay? Well, then we know what it means for a Lagrangian in this setting to be smooth. Well, what is it? Well, Lagrangian, which assigns to any field some top form, should be smooth if it defines, well, if it uniquely extends, let's say, to define, well, to act also on RK plots and give you, well,
Grigori, you want to tell the audience what that symbol is?
oh, again. Okay, this is my omega. Right. Ooh. Okay. So this is gonna be right. This is omega. This circle with an. Sorry. This is, yeah. This is omega. Just please bear with me. It just means top forms. If I change it all over now, it's gonna be a nightmare. Sorry. Yeah. Very bad. Okay. Well, it just says, yeah. These are sections of the top, well, of the top exterior part of the cotangent map, let's say. Okay. So top forms. That's what it means, right? And since this is sections of a bundle, it also has a smooth structure, as we said. This is sections of a bundle as well, so we should consider them both as smooth sets and demand that the Lagrangian is smooth in this sense. Okay? Well, then the integration is actually smooth. You can just check. It defines a smooth map. What do? Well, you take an RK parameterized top form, and you say, well, what does it map to? It should be a plot of the real numbers, which is, well, anyways, you can just write it down. Let me not go into details, but this is automatically smooth in this setting, this integration map. And then if you have a smooth Lagrangian, you can just compose with a smooth map. And because in any category, composition gives another map of that category, this is smooth again. Okay. And now in particular, we want to ask, what are local functionals, the way physicists write them down, right, with these partial derivatives, and are they smooth in this sense? And the answer is yes, but for that, we need to talk a bit about the infinite jet bundle. Maybe we don't need actually, maybe we only define a dimension, finite order, but let me talk about it just in case. Okay, let's get into it. Any questions? Okay. Well, the infinite jet bundle, let me just throw some facts on you so we can skip over it. Yeah. Okay, so here are some facts, okay? So this limit, so there exists a finite order jet bundle for any k in the natural numbers. And this is a finite dimensional manifold which has coordinates, well, let's say, if you go to first order jet bundle, you just have the coordinates of the base of the fiber and then an extra coordinate which encodes the derivative with respect to that fiber. If you go to the second order jet bundle, you have an extra coordinate which encodes second order derivatives and so on, roughly. And you can do this to any order, but then you want to say, okay, I want to take the limit of this. Right? Not in coordinates, but as something that is not only local, but a global object. So it's a limit of finite dimensional manifolds. Each order is finite dimensional, but the limit is not because the dimension increases. But in fact, this is a manifold in some sense. It's a Frechet manifold. It's an infinite dimensional manifold. And well, you can look into it. It's also paracompact for those who care. And it's important actually. Now here's an extra property of it. We don't need to worry about the details, but here's a property. Well, the smooth maps, Frechet maps in the Frechet sense, out of this guy into the real numbers, these are locally the pullbacks. So locally, they're actually maps from a finite order jet bundle. So you just pull back, pre-compose with the projection to get that. But only locally, not necessarily globally. But it includes that factor globally. Well, in any case, if you want in coordinates, this says that locally, these depend only on finitely many coordinates on the infinite jet bundle. So these expressions of the Lagrangian are included in there in a sense, its coefficients. So here is a slight generalization of that. Well, if the target is not the real numbers, but actually any finite dimensional manifold, which can be seen as a Fréchet manifold, then the same statement holds. Okay. And for instance, in particular, we want these kind of things. Well, bundle maps out of the infinite jet bundle into this finite dimensional manifold, which is just the top exterior power of the cotangent bundle of the base, is locally, by these results, is locally of this form. So you have some top form here, local coordinates, and then you have some coefficient, some function, depending on finitely many coordinates on the jet bundle. Okay, then the jet prolongation, which I don't have time to talk to, but it does what you think it does. It just plugs in here the value of the derivative of the field that you chose. Okay. Well, then precomposing by this guy locally, it looks like this. So you get exactly the form of Lagrangians that appear in physics. Right. So it amounts to the replacement of these coordinates. This is why you actually work with a jet bundle. It's an object that encodes these derivatives, let's say, along the fiber directions for fields, but it's an object by itself. And then you precompose with this and you get exactly this value for any field now, right? So for any choice of field, you get this kind of expressions, right? And the question now is this guy smooth? Now, maybe I will confuse you a bit more, but now, well, there is a notion of smoothness in Fréchet manifolds, but this does not include these field spaces that we talked about, okay? It says that this map is smooth, okay, and it has this form. However, it doesn't say anything about this jet prolongation because these spaces themselves are not Fréchet necessarily. Okay, so we want to go into, again, smooth sets, like we said, okay? And how do we do this? Well, we're lucky, actually, that Fréchet manifolds also faithfully embed into smooth sets. By the same formula that I wrote down for manifolds, finite dimensional manifolds, well, it's a theorem, that it's, this is also fully faithful. The formula is this. You don't need to worry too much about it. The point being is that, well, then you can view the infinite jet bundle as a smooth set as well, if you want, and the sections of that bundle. Right? For instance, you embed the infinite jet bundle, you embed the space-time as well, and then this is, well, a bundle in smooth sets, let's say. So it's a map with smooth sets. So you can consider sections of this guy. Let me not go through it, but sections of this guy now, smooth sections, are also a smooth set by the same formulas as before. Okay, so we have a notion. This space here becomes also, this set becomes smooth as well. And then it follows by the limit property of this guy, whatever that means for those who understand, by the universal property of this guy, it follows really that this thing is also smooth necessarily, it just defines a smooth map. Right, recall this is just sections of the original bundle, and this maps into sections of the infinite jet bundle. Right? And furthermore, bundle maps as such, they necessarily define, these are little results, you can check. They do define smooth maps of smooth sets. Okay. So we jumped into smooth sets and it includes everything we want, right? So it includes field spaces, jet bundles, infinite jet bundles, jet prolongations, everything is smooth in there. So it follows that by just composing smooth maps, that the local Lagrangians, as written in physics, are indeed smooth, like maps of smooth sets. So you take a field, you take its jet prolongation, or let's say an RK plot of fields, you take the jet prolongation and you compose with a bundle map, L, and you get something smooth. Furthermore, you compose with a smooth map of integration, you get again something smooth. In particular, well, for any line plot, so for any R1 parameterized section of fields, family of fields, well, you can apply the action function on it and you end up getting really a smooth map from the reals into the reals. So we can take the derivative rigorously. Okay, I'll go a bit faster because people I don't think they care, but let me finish with this. Here's a proposition, then a rigorous, let's say, proposition. Well, for any local action functional of this form, viewed as a map of smooth sets, well, then, well, this becomes a rigorous statement that a point, so a point plot, let's say, in fields is critical if and only if it satisfies the Euler-Lagrange equations. Well, you can also define critical RK plots now, not only point plots, but you can define a notion of critical RK plot by saying, well, it's RK plots such that curves or one parameter families of RK plots satisfy the same condition. And you can prove that it's if and only if the Euler-Lagrange operator, viewed as extended vertically, well, it satisfies again the Euler-Lagrange field equations. And then by staring at these formulas, you can realize that the critical plots, this assignment of critical RK plots, they do indeed form a smooth set. So it's some smooth subspace of the full field space given by this pullback, which exists now in smooth sets. So you have this smooth space of fields, and you have this section, this space of sections of some bundle, it's also a smooth space. And you have a map here, a smooth map, a zero map, fiber map. And you have this differential operator, which naturally, also I didn't say, but it's also a smooth map naturally. And then you can form this intersection in smooth sets where it exists. So this is exactly what it says. So everything becomes rigorous in here. And let me just bombard you with some more results that but it's not just doing. Well, anyways, everything in physics that people write down in this it really takes place in this setting. Let's say at least classically. So currents or p-form currents, which you integrate over submanifolds or in submanifolds compact, they are smooth as functions on the field space. The charges are also smooth. The on-shell conserved currents and charges are also smooth as maps. You know, when you consider the smooth structure that I just described on the classical space of on-shell fields, there's natural notions of diffeomorphism, smooth vector fields, tangent vectors, tangent bundles, and so on. And these do encode local diffeomorphism vector field symmetries in the classical sense. The formulas just come out. Noether's first and second theorems are really about local symmetries and, in this sense, smooth symmetries on field space. And the currents they produce are also smooth. So let me stop there. Are there any questions? And maybe I can give an outlook if we're early. If
Also will be in the paper.
yeah, these extra fruits are going to be in the paper. Otherwise it would be a very short paper. Maybe. Any other questions? Well, let me then bombard you again with some outlook. All right, so what did we do now, right? So we described this generalized notion of smooth spaces by saying how it is to smoothly probe something, right? This can be generalized for whatever needs you have, for whatever thing you want to describe, right? So in particular, we can generalize it in part 2 of this series. We want to have an intrinsic notion of perturbation theory, let's say, for physics. Like in physics we do, right? This expansion around the fixed point in field space, and you take this formal perturbation theory, like the Taylor expansion in some sense, generalized sense. And we want to do this rigorously in this kind of notion of field spaces. Well, how do you do this? Well, you really want to, how do you define these infinitesimal neighborhoods properly? What you need to do is you enrich the site, the things that we use to probe our would-be spaces, you put more things in there, more probes, and this should detect infinitesimal behavior. So this should be infinitesimal thickened points in a precise sense. So this is in particular a model for synthetic differential geometry. And in there is a natural definitions for tangent vectors and tangent bundles, very like complete natural, and the physical things come out. It's not just random, it's not a notion, it's like you get automatically the tangent bundles used in physics. And so vector field symmetries, blah, blah, blah. The jet bundles and the infinite one can be defined internally without talking about Fréchet stuff at all. So it's do some categorical mambo jumbo. There is spaces, more general spaces that serve as classifying spaces for differential forms in a precise sense. You can define, you have a definition of a Cauchy surface that the physics have. Well, some manifold with initial conditions data on it. This can be made precise as some object in here, in this category. And really, infinitesimal neighborhoods exist as things. So in particular, there's subspaces in this generalized sense of the field space. Or if you want, if you take this to be a finite dimensional manifold, this would really correspond to an the jet algebra, let's say, the spec of that thing. So really, it does what you expect. The Taylor series stuff does correspond to infinitesimal neighborhoods. And in particular, perturbation theory in local field theories, right, it's just a restriction to the infinitesimal neighborhood, and you really get out these expansions. Okay, further, you can also, you want to include fermions, and right, so what we said up to now is only for bosons, really. All the formulas we wrote down, everything is really about bosons. But in physics, people write down this kind of formulas, right? So you write this formula for a fermion on the line, let's say, right? But this formula, well, you want to say, what is this symbol psi here? And you stare at it enough, you realize, well, it's quite confusing if it's the first time you see it. Well, if you integrate it by parts, if it was just a section of a bundle, or if it was a real valued map into a vector space, smooth map, well, if you integrate by parts, then this would be 0. So we have no dynamics. But then you want this to anti-commute so that it's not 0. And what does it mean for this symbol to anti-commute? Well, what is it exactly? Well, you say maybe it's a map of supermanifolds where you take this vector space to be odd, so some oddness comes in. But by definition, a map of supermanifolds from the real line into something odd is nothing, because it has to preserve the grading. So anyways, you go through these things, and you realize that, well, this kind of symbol that people write down is really denotes an arbitrary RPQ plot. So let's say maybe where this is the super Cartesian space. I will not say much about it. Of the super mapping space, smooth mapping space, given as such. Well, what is this? Well, this should be something then. It's sheaves again. You enrich again your probes by putting these odd probes, so these fermionic probes. So this is really, I mean, this is not something that, you know, someone comes up to do weird stuff. Really, you just want to see what this formula is. What is it, like, mathematically? And sort of, you just stare it enough, you play with these formulas, and you will see that really what it is, it's this kind of thing. It's sheaves, it's plots of this space, which is a sheaf over super Cartesian spaces. Okay. So in particular, in this setting, you can describe fermions, local fermionic field theory. You can talk about jet bundles of odd bundles. You can talk about local fermionic bosonic Lagrangians, right? This has nothing to do with supersymmetry. It doesn't presume supersymmetry in the dynamics. It's just also the standard model has this feature. It has these terms in there, and people don't care about them. But what do they mean? They mean this. Well, you can interpret it differently, but this is the simplest way, I think. Yeah. Okay, furthermore, we will do more stuff. If you want to talk about gauge fields, non-perturbatively, so if you want to, for instance, connections on bundles or higher bundles, and you want to take topology into account, yeah, really, you should, you know, the space of fields, all connections does not really form a set. It forms a groupoid, or for higher stuff, higher groupoids. And so you want to talk about things that are thick. Well, your spaces would be not just, well, sheaves on thickened super Cartesian probes, but they should be higher sheaves. So it should be functors into simplicial sets, so, or some subcategory of that, or and so on, some higher notion. And then furthermore, if you want to talk about quantization, let me not go through it, but if you have gauge symmetries as such, then you don't have Cauchy surfaces, then there is no symplectic phase space, then there is no geometric quantization. So you would like to replace your theory with something that is weakly or homotopically equivalent to it, such that you have no gauge symmetries and such that you can do geometric quantization, if you could, so that then you have some symplectic phase space and you can go through the process. But then really, what you end up with, if you take this into account properly, is BV-BRST formalism of physics. It's really talking about this higher derived notion of super smooth geometry and where you talk about higher versions, homotopical versions of quotients, intersections, and so on, which I'm not gonna say anything about. But anyways, my point is that, right, once you want to do something more general, as it is that your purposes dictate, you enlarge your site usually, or maybe your target as well, but you usually enlarge your site to encode these extra spaces of would-be spaces that you'd like to. Anyways, so this is the rough story. Hopefully someone got something out of it.
Okay. Great. Thank you, Grigorios.
Good talk, Greg.
Oh, thank you.
Questions? I was gonna ask what's next, but you already outlined what's next.
Yeah, we had 5 minutes, so I thought I might as well.
This is good. Okay, so then perhaps there will be questions when the paper is out or afterwards.
Sure.
Okay, great. Thank you so much.
Thank you.